Look up on a clear night, far from city lights, and you'll see it. A luminous band stretching across the sky, a river of stars so dense they blur together into a continuous glow. The ancients saw spilled milk, a celestial pathway, the backbone of night itself. We call it the Milky Way, our home galaxy, a vast spiral of hundreds of billions of stars rotating through the cosmic darkness. But here's what's strange. What's been troubling astronomers for nearly a century? The Milky Way shouldn't exist, not in the form we observe it. The stars we see, the gas clouds glowing in nebulae, the dust lanes threading through spiral arms, all the ordinary matter we can detect through telescopes, adds up to a galaxy that should have torn itself apart billions of years ago. The rotation is too fast. The gravity from visible matter is insufficient. By all rights, stars in the outer regions should have been flung into intergalactic space long ago, scattered like water droplets from a spinning wheel. Yet, the galaxy holds together. The stars remain in their orbits. The spiral structure persists across billions of years. Something is keeping it all bound, providing the gravitational glue that prevents cosmic disintegration. That something is dark matter invisible, undetectable by any telescope, interacting with ordinary matter almost exclusively through gravity. It doesn't emit light, doesn't absorb light, doesn't reflect light. It passes through normal matter like a ghost through walls, yet it outweighs everything we can see by a factor of 6 to 1. For every kilogram of stars, planets, gas, and dust, there are 6 kilograms of dark matter, silent and unseen. This isn't speculation or exotic theory proposed at the fringes of physics. Dark matter is established science, supported by multiple independent lines of evidence, from galactic rotation curves to gravitational lensing to the cosmic microwave background. The observations are unambiguous. Something invisible is out there, shaping the universe we inhabit, holding galaxies like ours together through gravitational influence alone. Tonight, we're pursuing a question that bridges astrophysics and cosmic mystery. Not whether dark matter exists, the evidence for that is overwhelming. Not simply what it might be made of, though we'll explore the leading candidates. But specifically, how does dark matter hold the Milky Way together? What is its distribution through our galaxy? How does it interact with the visible structures we observe? What would happen if it suddenly disappeared? And why, after decades of searching, have we still not detected a single dark matter particle directly? This investigation will take us from the first hints of invisible mass in the 1930s to modern particle detectors buried miles underground. We'll explore the halo of dark matter enveloping our galaxy, the cosmic web stretching between galaxies, the computer simulations revealing how structure forms in a dark matter-dominated universe. We'll examine the evidence from gravitational lensing, from satellite galaxies orbiting the Milky Way, from the precise motions of stars measured by space telescopes. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Your presence here, whether you're listening in the quiet hours before dawn or in the peaceful moments before sleep, it matters more than you know. Now let's begin with a problem that wouldn't make sense for half a century. Picture the solar system for a moment. Mercury races around the Sun at 47 kilometers per second, completing an orbit in just 88 days. Venus moves slower, 35 kilometers per second, taking 225 days per orbit. Earth cruises at a more leisurely 30 kilometers per second, 1 year per orbit. Mars moves at 24 kilometers per second. Jupiter at 13. Neptune, out in the distant reaches of the solar system, plods along at just 5 kilometers per second, taking 165 years to complete a single orbit. There's a pattern here, a mathematical relationship that's been understood since Kepler worked out his laws of planetary motion in the early 1600s. The farther you are from the Sun, the slower you orbit. This isn't arbitrary. It follows directly from Newton's law of gravity. The gravitational force decreases with the square of distance, so objects farther from the Sun experience weaker gravitational pull. To remain in a stable orbit at greater distance, they must move more slowly. The relationship is precise. Orbital velocity is proportional to 1 over the square root of distance. Double your distance from the Sun, and your orbital velocity decreases by a factor of the square root of 2, about 1.4. This same principle applies to any system where most of the mass is concentrated at the center and objects orbit around it. Moons orbiting planets, artificial satellites orbiting Earth, stars orbiting the center of globular clusters, they all follow this pattern. We call it a Keplerian decline, and it's one of the most fundamental relationships in orbital mechanics. In the 1970s, astronomer Vera Rubin, working with instrument builder Kent Ford at the Carnegie Institution of Washington, began making precise measurements of rotation in spiral galaxies. This was painstaking work requiring long exposure times on photographic plates and careful analysis of spectral lines to determine how fast stars and gas clouds were moving. Rubin and Ford focused on the Andromeda Galaxy, our nearest large spiral neighbor, using the Doppler shift of light to measure velocities at different distances from the galactic center. What they expected to find was a Keplerian decline. Most of a galaxy's visible matter, stars, gas, dust, is concentrated in the bright central bulge and disk. Based on the distribution of visible matter, stars in the outer reaches of the galaxy should be orbiting slowly, just like Neptune orbits the Sun slowly compared to inner planets. You could calculate the expected velocity at any radius by adding up all the visible matter interior to that radius and applying Newton's laws. What they actually found was completely different. The rotation curve, a graph showing orbital velocity versus distance from the galactic center, didn't decline at all in the outer regions. Instead, it stayed flat, remaining constant or even increasing slightly all the way out to the edge of the visible galaxy and beyond. Stars, hundreds of thousands of light years from the center, were moving just as fast as stars much closer in, around 200 kilometers per second, when they should have been moving at perhaps 50 or 60 kilometers per second based on the visible mass. This wasn't a small discrepancy. This wasn't measurement error or observational uncertainty. The velocities were far too high, by factors of 3 or 4, consistent across the entire outer region of the galaxy. And it wasn't just Andromeda. As Rubin and other astronomers studied more galaxies, dozens, then hundreds, they found the same pattern over and over. Spiral galaxy after spiral galaxy showed flat rotation curves where Keplerian decline should have been obvious. Elliptical galaxies showed similar problems when astronomers measured the velocities of stars and hot gas within them. The pattern was universal. There were only two possible explanations. Either Newton's laws of gravity, which had been tested countless times over 3 centuries and which worked perfectly for everything from falling apples to planetary orbits to the trajectories of spacecraft, somehow broke down on galactic scales. Or there was additional mass in these galaxies. Mass that didn't shine, mass that couldn't be seen, but whose gravitational influence was keeping stars moving fast in the outer regions. The scientific community was initially skeptical. Invisible mass? It seemed ad hoc, a desperate attempt to save the appearances rather than face the possibility that gravity worked differently on large scales. Some physicists proposed modifications to Newtonian gravity, theories where the force law changed at very low accelerations, typical of the outer regions of galaxies. These modified Newtonian dynamics theories, collectively called MOND, could reproduce flat rotation curves without invoking dark matter. But as evidence accumulated from multiple independent observations, the dark matter hypothesis became increasingly compelling while alternative theories struggled to explain all the data. The rotation curves were just the beginning, the first clear hint that something invisible was out there. Soon, other evidence would emerge that would transform dark matter from controversial hypothesis to established fact. Let me tell you about a man who saw the problem decades earlier, though almost no one listened at the time. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies about 320 million light-years from Earth. Using the Mount Wilson Observatory's telescopes, he measured the velocities of individual galaxies within the cluster through Doppler shifts. What he found troubled him deeply. The galaxies were moving far too fast. They zipped through the cluster at speeds of hundreds to thousands of kilometers per second. When Zwicky calculated how much mass the cluster needed to gravitationally bind these fast-moving galaxies to prevent them from escaping the cluster entirely, he got a number roughly 400 times larger than the mass of all the visible galaxies combined. Zwicky called this missing mass Dunkel Materie, dark matter. He proposed that most of the cluster's mass was in some form that didn't produce light, invisible material providing the gravity necessary to hold everything together. The scientific community largely ignored Zwicky's claim. He was known as difficult, combative, prone to radical ideas. His personality didn't help his case. And in the 1930s, there was no framework for thinking about what this dark matter might be, no particle physics context to make sense of it. It seemed easier to assume Zwicky had made an error or that there was some mundane explanation. Perhaps the galaxies weren't gravitationally bound, or perhaps there was more regular matter in the form of dim stars and gas than could easily be detected. By the 1980s, between the rotation curve observations and new measurements of galaxy clusters using better techniques, the evidence had become overwhelming. Dark matter was real. Galaxies were embedded in massive halos of invisible stuff that outweighed the visible matter by factors of 5 to 10. But what about the Milky Way specifically? We've been talking about other galaxies, systems we observe from outside. Can we detect dark matter in our own galaxy? The answer is yes, but it's more complicated. We're inside the Milky Way, embedded within its disk, which makes certain measurements harder but others easier. We can't step back and look at the galaxy as a whole the way we can with Andromeda. But we can measure the motions of stars around us with exquisite precision, and we can map the distribution of matter in 3 dimensions rather than projecting it onto the 2-dimensional sky. Astronomers can trace the Milky Way's rotation curve from the inner galaxy out to distances of 60,000 light-years or more, using various tracers, hot stars, gas clouds, globular clusters. The curve stays relatively flat across this entire range, just like other spiral galaxies. This tells us the Milky Way is embedded in an extended dark matter halo, a roughly spherical distribution of invisible mass that extends far beyond the visible stellar disk. But we can go further. We can study individual stars and their orbital motions to map the gravitational field in 3 dimensions. The European Space Agency's Gaia mission, launched in 2013, is measuring the precise positions and velocities of nearly 2 billion stars in the Milky Way. This unprecedented dataset allows astronomers to determine not just how fast stars are moving, but in what directions, building a complete picture of motion throughout the galaxy. The precision of Gaia's measurements is staggering. For the brightest stars, Gaia can measure positions accurate to a few millionths of an arcsecond, equivalent to measuring the width of a human hair from 1,000 kilometers away. More importantly, by measuring the same stars repeatedly over years, Gaia tracks their motion across the sky, determining not just where they are, but where they're going. Combined with spectroscopic measurements of their velocities along our line of sight, this creates a complete 3-dimensional map of stellar motion. These measurements reveal something fascinating. The dark matter halo isn't perfectly smooth or perfectly spherical. It has structure, possibly even streams and clumps left over from the galaxy's formation history. When smaller galaxies fell into the Milky Way's gravitational well billions of years ago, they brought their own dark matter halos with them. These halos were stretched and torn apart by tidal forces, creating streams of dark matter flowing through the galaxy in particular patterns. The Gaia data shows evidence of these streams in the motions of stars. Stars that originated in the same dwarf galaxy billions of years ago, stars that have now been scattered across the sky, still share similar velocities because they're all moving through the same gravitational field shaped by dark matter. By studying these coherent motions, astronomers can map the dark matter distribution indirectly, seeing its gravitational fingerprints in stellar kinematics. Consider what this means. A star that was once part of a small dwarf galaxy orbiting peacefully in the outskirts of the young Milky Way 10 billion years ago has since been scattered halfway across the galaxy by tidal forces. Yet its velocity, its speed and direction through space still carries information about the dark matter structure it's moving through. By finding hundreds or thousands of stars with similar velocities, astronomers can identify them as members of the same ancient population and use their collective motion to infer properties of the invisible dark matter streaming around them. There's another way to probe the Milky Way's dark matter: satellite galaxies. The Milky Way isn't alone. It's surrounded by dozens of smaller galaxies gravitationally bound to it, orbiting through the dark matter halo like planets around a star. The largest are the Large and Small Magellanic Clouds, visible as fuzzy patches in the southern hemisphere's sky. Others are tiny dwarf spheroidal galaxies containing only thousands or tens of thousands of stars, barely distinguishable from globular clusters. These satellite galaxies are sensitive probes of the gravitational field. Their orbits depend on the total mass distribution of the Milky Way, both visible and dark. By measuring their positions and velocities precisely, by tracking how they move over time, astronomers can infer the mass and shape of the dark matter halo. What these studies reveal is striking. The Milky Way's total mass, including dark matter, is somewhere between 800 billion and 1.5 trillion solar masses. Of this, only about 60 billion solar masses is in stars, perhaps another 10 to 20 billion in gas and dust. The dark matter halo extends to at least 600,000 light-years from the galactic center, possibly much farther. For comparison, the visible stellar disk is only about 100,000 light-years across. We're embedded in a vast sphere of invisible mass that dwarfs the visible galaxy, a cocoon of darkness holding everything together through gravitational influence alone. But why should this be? Why is the universe constructed this way, with visible matter as a minority component embedded in dominant dark matter? To answer that, we need to understand how galaxies form, how structure emerges from the smooth early universe. We need to go back to the beginning. The universe began 13.8 billion years ago in the Big Bang, emerging from an incredibly hot, dense state and expanding rapidly. In the first moments, the cosmos was almost perfectly smooth, with matter and radiation distributed nearly uniformly throughout space, but not quite perfectly. There were tiny fluctuations, random quantum variations in density from one region to another, differences of perhaps 1 part in 100,000. These tiny fluctuations were imprinted in the cosmic microwave background, the afterglow of the Big Bang that we observe today as faint radio waves coming from every direction in the sky. Space telescopes like COBE, WMAP, and Planck have mapped these fluctuations with extraordinary precision, creating baby pictures of the universe when it was only 380,000 years old, long before any stars or galaxies formed. The cosmic microwave background reveals something crucial. The early universe was smoother than it should have been. The fluctuations we observe are smaller than what would be expected if only ordinary matter was present. This smoothness is a problem for galaxy formation because galaxies require density fluctuations to grow. Regions slightly denser than average attract more matter through gravity, becoming denser still, eventually collapsing to form stars and galaxies. But if the fluctuations are too small, if the universe is too smooth, there hasn't been enough time since the Big Bang for galaxies like the Milky Way to form through gravitational collapse of ordinary matter alone. Dark matter solves this problem. Unlike ordinary matter, dark matter doesn't interact with light or radiation. In the early universe, before stars formed, ordinary matter was coupled to radiation through electromagnetic forces. Photons constantly scattered off electrons and protons, creating pressure that resisted gravitational collapse. This radiation pressure smoothed out density fluctuations in ordinary matter, preventing them from growing efficiently. But dark matter was immune to this pressure. It didn't interact with photons, didn't feel electromagnetic forces. While ordinary matter's fluctuations were being smoothed by radiation pressure, dark matter's fluctuations could grow unimpeded through gravitational instability. Dense regions of dark matter became denser, collapsing into clumps and halos, while ordinary matter remained smooth and spread out. The timeline of this process is crucial to understanding why dark matter was so important. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma. Ordinary matter protons, electrons, helium nuclei was thoroughly mixed with photons, creating a thick fog that was opaque to light. Any attempt by ordinary matter to collapse under gravity was immediately counteracted by radiation pressure pushing outward. It was like trying to compress a spring. The harder gravity pushed inward, the harder radiation pressure pushed back. Dark matter faced no such resistance. From the earliest moments, dark matter particles were decoupled from radiation. They felt only gravity, responding only to the tiny density fluctuations imprinted during cosmic inflation. In regions where dark matter was slightly denser than average, even by 1 part in 100,000, gravity slowly pulled more dark matter in. These overdense regions grew, their gravity becoming stronger, attracting even more dark matter in a positive feedback loop. By the time the universe reached 380,000 years after the Big Bang, the moment when ordinary matter finally decoupled from radiation and the cosmic microwave background was released, dark matter had already created. Significant structure. Dark matter halos had collapsed, creating gravitational potential wells scattered throughout the universe. These wells were like valleys in the gravitational landscape, ready to trap any ordinary matter that wandered nearby. When ordinary matter decoupled from radiation, it suddenly became free to respond to gravity without radiation pressure fighting back. And the gravitational landscape it found itself in was shaped entirely by dark matter. Ordinary matter, hydrogen and helium gas began flowing into the dark matter potential wells, falling down the valleys that dark matter had carved into the fabric of space-time. This is the key to understanding galaxy formation. Dark matter provided the gravitational scaffolding, the framework of invisible mass that attracted ordinary matter and allowed it to collect and form galaxies. Without dark matter, galaxies like the Milky Way couldn't have formed in the time available since the Big Bang. The universe would still be smooth and featureless, or at least far less structured than what we observe. Computer simulations bear this out dramatically. When astrophysicists simulate the evolution of the universe from the Big Bang to the present, they need to include dark matter to reproduce the observed distribution of galaxies. Simulations with only ordinary matter produce a universe that looks nothing like the one we inhabit, too smooth, too homogeneous, with far fewer galaxies and different structure. Simulations including dark matter, by contrast, produce a universe remarkably similar to observations. They show dark matter organizing itself into a vast cosmic web, with dense nodes connected by filaments stretching across hundreds of millions of light years, separated by vast voids containing almost nothing. Galaxies form at the nodes and along the filaments, where dark matter is most concentrated, following the gravitational potential wells created by the invisible scaffolding. The largest of these simulations track billions of dark matter particles and millions of galaxies across cosmic time, from shortly after the Big Bang to the present day. They reveal how structure grows hierarchically, with small dark matter halos forming first, then merging to build larger halos, which merge to build still larger systems. Galaxies form within these halos, growing as gas cools and condenses at the centers, igniting stars, developing spiral arms and central bulges. These simulations can zoom in on individual galaxy-sized dark matter halos and study their properties in detail. What they show is that dark matter halos aren't uniform spheres, but complex structures with particular density profiles. The density is highest at the center and decreases toward the outskirts following what's called an NFW profile, named after Navarro, Frank, and White, the physicists who first characterized it in simulations. This profile has been confirmed through observations of galaxy rotation curves and gravitational lensing, providing strong evidence that the simulations are capturing something real about how dark matter organizes itself. The Milky Way formed this way, through the hierarchical assembly of dark matter and ordinary matter over billions of years. About 13 billion years ago, in a region of space that would eventually become our local neighborhood, a dark matter halo began to condense. This halo grew as smaller halos merged into it, bringing both dark matter and gas that would eventually form stars. The ordinary matter behaved differently from dark matter in crucial ways. While dark matter remained distributed throughout the halo in a roughly spherical configuration, ordinary matter could lose energy through radiation. When gas clouds collided, they heated up and emitted photons, carrying energy away. This allowed ordinary matter to cool and sink deeper into the gravitational potential well, condensing toward the center where it formed a rotating disk. This is why galaxies like the Milky Way have the structure they do: an extended dark matter halo that's roughly spherical, and a flattened disk of ordinary matter, stars and gas at the center. The dark matter couldn't condense into a disk because it had no way to lose energy. Individual dark matter particles just orbit through the halo on elongated paths, passing through the galactic disk without interacting, creating a smooth gravitational field. The Milky Way's formation wasn't smooth or quiet. It experienced numerous mergers with smaller galaxies, violent interactions that stirred the stellar populations and scattered stars into the halo. The most recent major merger occurred about 8 to 10 billion years ago when a substantial dwarf galaxy called Gaia Enceladus collided with the young Milky Way. This merger brought perhaps 1 billion solar masses of stars and a substantial dark matter halo into our galaxy. The stellar remnants of Gaia Enceladus can still be identified today through chemical composition and orbital patterns discovered through analysis of Gaia satellite data. These merger events shaped not just the visible galaxy, but the dark matter halo as well. Each infalling dwarf galaxy brought its own dark matter, which merged with the Milky Way's halo. But because dark matter doesn't interact electromagnetically, it doesn't mix smoothly. Instead, it can form streams and substructures that persist for billions of years, fossil remnants of ancient merger events. The cosmic web framework explains why dark matter is so dominant. It had a head start, collapsing early when ordinary matter was still prevented from clumping by radiation pressure. By the time ordinary matter could collapse and form stars, dark matter had already created the gravitational potential wells that determined where galaxies would form and how large they would become. The visible galaxies we see are like foam on ocean waves, noticeable and interesting, but representing only a small fraction of the total mass and energy driving the system. This means that to understand why the Milky Way exists where it does, why it has the mass it does, why it moves through space in the direction it does, we need to understand the dark matter structures within which it formed. The galaxy's position in the cosmic web, its trajectory through space, its interaction history with neighboring galaxies, all of these are determined primarily by dark matter dynamics that began operating billions of years before the first stars formed. But cosmic web simulations and galaxy formation theory only take us so far. They tell us dark matter should be there, that it plays a crucial role in structure formation. They don't tell us what it is. For that, we need to venture into particle physics, to explore what kinds of particles could constitute the invisible mass holding galaxies together. The search for dark matter's identity has become one of the great scientific quests of our time, involving particle physicists, astronomers, and cosmologists, employing detectors from deep underground to orbital space telescopes. Despite decades of effort and increasingly sophisticated experiments, dark matter particles remain frustratingly elusive. Let's explore what we do know about what dark matter can and cannot be, narrowing down possibilities and understanding why the leading candidates are what they are. First, dark matter isn't ordinary matter. By ordinary matter, physicists mean matter made of protons, neutrons, and electrons, the stuff that makes up atoms, molecules, stars, planets, you and me. Physicists call ordinary matter baryonic matter because protons and neutrons are baryons, particles made of three quarks bound together by the strong nuclear force. How do we know dark matter isn't baryonic? Several lines of evidence converge. First, observations of Big Bang nucleosynthesis, the formation of light elements like hydrogen, helium, and lithium in the first few minutes after the Big Bang tightly constrain how much ordinary matter can exist in the universe. The relative abundances of these elements depend sensitively on the density of protons and neutrons during nucleosynthesis. Measurements show that baryonic matter makes up only about 5% of the universe's total mass energy. Dark matter is 26 or 27%. The numbers don't match. Dark matter must be something else. Second, massive compact halo objects, MACHOs, were once considered as dark matter candidates. These would be ordinary matter in forms that don't shine. Brown dwarfs, planets, neutron stars, black holes, white dwarfs, or any other object made of protons and neutrons but too dim to detect directly. In the 1990s and early 2000s, several surveys searched for MACHOs by looking for gravitational microlensing events. Brief brightenings of background stars when a massive dark object passes in front of them, bending light through gravitational lensing. These surveys found some microlensing events, but far too few to account for the Milky Way's dark matter. MACHOs might contribute perhaps 20% of the dark matter in the galactic halo at most, probably much less. They cannot be the primary component. So dark matter must be something more exotic. The leading candidate by far is a class of hypothetical particles called weakly interacting massive particles, WIMPs. The name describes their key properties. They're massive, meaning they have significant rest mass rather than being massless like photons, and they interact weakly, meaning they don't participate in electromagnetic or strong nuclear interactions, but only feel gravity and possibly the weak nuclear force. WIMPs emerged as dark matter candidates from particle physics theories developed for other reasons. In the 1970s and 80s, physicists working on supersymmetry, a theoretical framework extending the standard model of particle physics, realized their theories naturally predicted stable particles that had exactly the properties needed for dark matter. These supersymmetric particles would be massive, typically 10 to 1,000 times the mass of a proton, and would interact only through gravity and the weak force. What makes WIMPs particularly compelling is something called the WIMP miracle. When you calculate how many of these particles would have been produced in the early universe, considering their interaction rates and the expansion of space, you get a relic density remarkably close to the observed dark matter density. This wasn't designed into the theory. It emerged naturally from the physics. The fact that supersymmetry developed to solve completely different problems in particle physics predicted particles with just the right properties and abundances to be dark matter struck many physicists as too much of a coincidence to ignore. If WIMPs exist, they should be passing through Earth constantly. The Milky Way's dark matter halo extends through the solar system. The Sun, Earth, and all the planets are moving through this dark matter at about 220 kilometers per second as we orbit the galactic center. This means a flux of dark matter particles constantly streams through our bodies, through buildings, through the Earth itself. If a typical WIMP weighs about 100 times a proton mass, and the local dark matter density is about 0.3 GeV per cubic centimeter, roughly 300,000 times less dense than air, but still substantial when integrated. Over the vast volume of the dark matter halo, then roughly 10 billion WIMPs pass through your body every second. The vast majority pass through without interacting. But very occasionally, perhaps once in a while for your entire body over a human lifetime, a WIMP might scatter off a nucleus in one of your atoms. This scattering would be incredibly gentle. The nucleus would recoil with energy equivalent to just a few electron volts, far too little to cause any biological effect. But in principle, this interaction could be detected with sufficiently sensitive equipment. This is the basis of direct detection experiments. If you build a detector with enough target mass, shield it carefully from backgrounds like cosmic rays and natural radioactivity, and make it sensitive enough to detect the tiny energy deposited when a WIMP scatters off a nucleus, you might observe dark matter interactions directly. Dozens of experiments around the world are attempting exactly this. They're typically located deep underground in mines, under mountains, in specially built laboratories where thousands of meters of rock shield them from cosmic rays that would otherwise create overwhelming background noise. The detectors use various target materials: liquid xenon, liquid argon, germanium crystals, sodium iodide crystals, superheated liquids. Each has advantages and disadvantages in terms of sensitivity, background rejection, and energy resolution. The largest and most sensitive experiments, like Xenont in Italy and Lux Zeppelin in South Dakota, use tons of ultra-pure liquid xenon as target material. When a WIMP scatters off a xenon nucleus, the nucleus recoils, creating both scintillation light and ionization electrons that can be detected with extreme precision. By measuring both signals, experimentalists can distinguish nuclear recoils from electron recoils caused by background radiation, pulling the dark matter signal out of the noise. After decades of searching with ever more sensitive detectors, no dark matter signal has been convincingly detected. The experiments have set stringent upper limits on how strongly WIMPs can interact with ordinary matter. These limits have ruled out the simplest WIMP models, the most straightforward supersymmetric candidates. If WIMPs exist, they must interact even more weakly than initially expected, or have masses outside the range where detectors are most sensitive. This null result has frustrated the field, but hasn't eliminated WIMPs as candidates. The interaction strength of dark matter with ordinary matter could be far weaker than the natural supersymmetric scale. Or dark matter might not be WIMPs at all, but something else entirely. One alternative is axions, hypothetical particles that are much lighter than WIMPs, with masses perhaps a millionth of an electron volt. Axions were proposed in the 1970s to solve a problem in the theory of the strong nuclear force called the strong CP problem. Like WIMPs from supersymmetry, axions emerged from particle theory developed for other reasons and turned out to have properties suitable for dark matter. Axions would behave differently from WIMPs. They'd be produced through different mechanisms in the early universe, exist in much higher numbers but with much lower individual masses, and interact with ordinary matter in different ways. Rather than scattering off nuclei, axions could convert into photons in strong magnetic fields. Several experiments, including ADMX and Haystack, use this principle, creating powerful magnetic fields and looking for faint radio signals that would indicate axion to photon conversion. Like direct detection WIMP searches, axion searches have so far come up empty. But they're covering only portions of the vast parameter space where axions might exist. The search continues, with improved sensitivity and wider mass ranges. There are other candidates: sterile neutrinos, gravitinos, dark photons, various particles predicted by string theory. Each has theoretical motivation and experimental signatures. Each requires different detection strategies. The dark matter particle zoo is rich and diverse, reflecting both our ignorance and the creative fertility of particle physics theory. Some physicists have begun wondering whether dark matter might not be particles at all, but something more exotic. Primordial black holes formed in the early universe, modifications to gravity that mimic dark matter effects, or perhaps multiple types of dark matter particles working together. The lack of detection, despite decades of effort, has opened minds to possibilities that might have seemed far-fetched 20 years ago. But here's what's remarkable. Gravity is universal and well understood. Whatever dark matter is made of, we know how it gravitates. And gravitational effects are what make dark matter observable in the first place, what allows us to map its presence throughout the galaxy despite its invisibility at every other wavelength. To see how this works in practice, we need to examine one of the most powerful techniques for mapping dark matter: gravitational lensing. General relativity tells us that mass warps spacetime, and light traveling through warped spacetime follows curved paths. This effect, called gravitational lensing, was one of the first tests of Einstein's theory. During a solar eclipse in 1919, astronomers measured the positions of stars near the sun's edge and found they appeared shifted from their normal positions by precisely the amount Einstein's equations predicted, confirming that the sun's mass bends starlight passing nearby. This same effect operates on galactic scales, but far more dramatically. Galaxies, with their enormous masses including vast dark matter halos, create substantial space-time curvature. Light from more distant galaxies traveling toward Earth passes through this curved space-time, its path bent by the foreground galaxy's gravitational field. The result depends on the geometry. If a background galaxy lies almost directly behind a massive foreground galaxy or cluster from our perspective, the light can be bent so strongly that we see multiple distorted images of the background galaxy, sometimes stretched into arcs or even complete rings called Einstein rings. This is strong lensing, dramatic and visually striking, used to study the mass distribution of galaxy clusters and to discover some of the most distant galaxies in the universe. magnified by cosmic lensing into visibility. But more commonly, the lensing is weak, creating small distortions that slightly stretch and shear background galaxy images without producing multiple images. Any individual galaxy's distortion is too small to measure reliably. It might be intrinsically elongated rather than lensed. But by studying thousands of background galaxies and averaging their distortions, astronomers can map the foreground mass distribution with exquisite precision. This is weak gravitational lensing, and it's become one of the most powerful tools for studying dark matter. What makes lensing so valuable is that it's sensitive to all matter, visible and dark. The space-time curvature that bends light depends on total mass, regardless of whether that mass emits light. By mapping how background galaxies are distorted, astronomers map the total matter distribution of foreground structures, including dark matter that would be invisible by any other means. When these techniques are applied to galaxy clusters, the results are stunning. Maps of dark matter distribution show that clusters are dominated by smooth, extended halos of invisible mass, with galaxies like visible markers embedded within the dark matter. The dark matter distribution is surprisingly smooth compared to the clumpy distribution of galaxies, consistent with dark matter being non-interacting particles that don't collide or clump beyond what gravity alone produces. One of the most dramatic demonstrations of dark matter's existence through lensing came from the Bullet Cluster, two galaxy clusters that collided about 150 million years ago. When astronomers mapped the mass distribution through gravitational lensing and compared it to the distribution of hot gas observed through X-ray telescopes, they found the mass and gas were separated. The hot gas, which makes up most of the ordinary matter in clusters, slowed down during the collision, interacting electromagnetically and creating shock waves. But the dark matter halos pass through each other almost unimpeded, like two swarms of bees interpenetrating. The lensing maps show the mass dominated by dark matter centered on the galaxy positions, while the gas trails behind. This is exactly what you'd expect if dark matter is non-interacting particles, and it's extremely difficult to explain with modified gravity theories. The Milky Way itself is too close for these lensing techniques to work directly. We're inside its dark matter halo rather than observing it from outside. But astronomers can use lensing to study the dark matter halos of other galaxies similar to the Milky Way, building statistical samples that reveal typical halo properties. These studies show that galaxies like the Milky Way are embedded in dark matter halos extending to virial radii of about 200 kiloparsecs, roughly 650,000 light-years. The halo mass is typically 10 times the stellar mass, consistent with the 90% dark matter fraction we discussed earlier. The halos have the NFW density profile predicted by simulations, denser at the center and more diffuse in the outskirts. But there's something puzzling that emerges from these studies, something that's been bothering astrophysicists for years. Simulations predict that dark matter halos should have lots of small-scale structure clumps and subhalos, remnants of smaller halos that merged into larger systems. The hierarchical formation picture suggests every large halo should contain hundreds or thousands of these subhalos, mini dark matter clumps orbiting through the main halo. When astronomers look at the Milky Way's satellite galaxies, they find far fewer than simulations predict. The Milky Way has perhaps 50 to 60 known satellite galaxies, mostly tiny dwarf spheroidals. Simulations predict there should be hundreds or even thousands of dark matter subhalos massive enough to potentially host visible galaxies. This is called the missing satellites problem. Where are all the predicted dwarf galaxies? Have they failed to form stars, remaining dark? Have they been disrupted by tidal forces? Or is there something wrong with the simulations, some physics they're missing, that prevents small-scale structure from forming? Recent discoveries have complicated the picture. New surveys, particularly those using the dark energy camera and the Gaia satellite, have discovered many extremely faint dwarf galaxies orbiting the Milky Way, so dim they were missed by earlier searches. The count of satellites keeps increasing, bringing observations closer to theoretical predictions. But it's unclear whether the gap will close completely or whether a genuine discrepancy remains. There's a related problem called the core cusp problem. Simulations predict dark matter halos should have cuspy profiles with density steeply rising toward the center. But observations of dwarf galaxies and the inner regions of some spiral galaxies suggest the central density is flatter than predicted, a core rather than a cusp. The effect is most pronounced in small low-mass galaxies. Various solutions have been proposed. Maybe baryonic physics, supernovae, stellar feedback, gas outflows modifies the dark matter distribution in ways not captured in early simulations. Maybe dark matter has weak self-interactions that aren't purely gravitational, allowing dark matter particles to scatter off each other and redistribute energy, smoothing out cusps into cores. Or maybe the observations are subject to systematic errors that make cusps look like cores. Recent high-resolution simulations, including detailed treatment of star formation, supernova feedback, and black hole growth, have shown that baryonic processes can indeed flatten central dark matter profiles somewhat. The jury is still out on whether this completely resolves the core cusp problem or whether additional physics is needed. These puzzles illustrate something important. While we understand dark matter's large-scale behavior, its role in structure formation, its distribution in galaxy halos, its gravitational effects, we're still working out details at smaller scales. The interplay between dark matter and ordinary matter, the effect of galaxy formation on dark matter distributions, the nature of the smallest dark matter structures, these remain active areas of research. But they don't undermine the fundamental evidence for dark matter's existence. They're details, important details that will refine our understanding. But they don't change the basic picture that galaxies are embedded in massive dark matter halos that provide most of the gravitational mass holding them together. For the Milky Way specifically, we can go beyond just knowing dark matter is there. We can attempt to map it in 3 dimensions, to understand its local distribution, to look for substructure and streams left over from merger events. This requires using every observational tool available and combining multiple lines of evidence. The dark matter halo surrounding the Milky Way isn't perfectly smooth. It has structure, lumps and streams, fossil remnants of the galaxy's formation history. By carefully studying stellar motions and using the Gaia satellite's unprecedented dataset, astronomers are beginning to map this invisible scaffolding in 3 dimensions. One of the most significant structures is the Sagittarius stream. The Sagittarius dwarf spheroidal galaxy is currently being torn apart by the Milky Way's tidal forces. As it orbits, it leaves behind streams of stars and dark matter that wrap around the galaxy multiple times. These streams can be traced through stellar surveys, identifying stars that share similar positions, velocities, and chemical compositions, marking them as remnants of the disrupted dwarf galaxy. But the Sagittarius stream isn't just stars. It also includes dark matter from the dwarf galaxy's original dark matter halo. This dark matter creates gravitational perturbations that affect other structures in the galaxy. By studying these perturbations, how the Milky Way's disk wobbles in response to dark matter streams passing through it, how other stellar streams are deflected, astronomers can constrain the dark matter content and distribution of structures like the Sagittarius stream. The Gaia-Enceladus merger we mentioned earlier, which occurred 8 to 10 billion years ago, also left dark matter signatures. The stars from this ancient dwarf galaxy can still be identified through their chemical compositions and orbital properties. They're slightly enriched in certain elements and tend to move on particular types of orbits. These stellar populations trace the dark matter that came in with Gaia Enceladus, now fully mixed into the Milky Way's halo, but potentially showing coherent bulk motions or density enhancements in certain regions. Recently, using Gaia data combined with computer simulations, astronomers have started identifying what they call the Gaia sausage, a thick distribution of stars in the inner halo with highly radial orbits, meaning they plunge close to the galactic center and then swing out to large distances. These stars likely originated in a massive merger billions of years ago, possibly the Gaia Enceladus event. The dark matter associated with this merger would follow similar orbital patterns, creating a non-spherical component to the dark matter halo that's denser in some directions than others. These discoveries reveal that the Milky Way's dark matter halo isn't a simple, smooth sphere, but a complex structure built through mergers and shaped by interactions over billions of years. This complexity matters for dark matter detection experiments. If the local dark matter distribution is more lumpy than assumed, if there are streams of dark matter passing through the solar neighborhood with particular velocities, this could affect detection rates and might explain null results from some experiments while creating opportunities for others. There's also the question of the solar system's immediate neighborhood. The Sun is located about 27,000 light-years from the galactic center, roughly 2/3 of the way out from center to edge in the galactic disk. At this location, the dark matter density is estimated to be about 0.3 to 0.4 GeV per cubic centimeter, though there's considerable uncertainty. This translates to roughly 1/3 of a proton mass per cubic centimeter, incomprehensibly diffused by everyday standards, a density about 1 trillion times less than air, but sufficient to create substantial gravitational effects when integrated over galactic volumes. Some studies have suggested the local dark matter density might vary seasonally due to the solar system's motion through the galaxy. The Sun orbits the galactic center, but it also bobs up and down through the galactic plane with a period of about 60 million years. As it moves through the plane, it experiences changing dark matter density, potentially creating variations in the flux of dark matter particles through Earth. These variations would be tiny, but might in principle be detectable with sufficiently precise experiments over long timescales. There have even been proposals that dark matter density variations could affect terrestrial systems in measurable ways. When the solar system passes through the galactic plane, where stellar and dark matter density is highest, the increased gravitational perturbations might disturb comets in the Oort cloud, sending some into the inner solar system, potentially increasing impact rates on Earth. Some researchers have speculated this could contribute to periodic patterns in mass extinctions, though this remains highly controversial and speculative. What's certain is that dark matter is not just something existing in the outer reaches of the galaxy or in distant galaxy clusters. It's here in our neighborhood, passing through the solar system and Earth continuously. Every cubic meter of space around you contains dark matter, just a few particles per cubic meter on average, but real nonetheless. You're embedded in it, moving through it, experiencing its gravitational influence in every orbit the Sun makes around the galactic center. This local dark matter is what direct detection experiments are trying to observe. The detectors deep underground aren't looking for dark matter from distant galaxies. They're looking for the dark matter halo that surrounds and interpenetrates our galaxy, the same dark matter that keeps the Milky Way's stars in their orbits, prevents the galaxy from flying apart, shaped its formation billions of years ago. The fact that we can calculate the local dark matter density from astrophysical observations, predict particle flux rates, design experiments to detect individual particle interactions, this shows how far we've come in understanding dark matter, despite never having detected it directly. We've mapped its distribution across cosmic scales, understood its role in structure formation, constrained its properties through multiple independent observations, all while remaining ignorant of what it's made of at the particle level. It's as if we were astronomers before the invention of the telescope, knowing stars exist through their light and warmth, understanding some patterns in their motions, but unable to resolve them as individual objects or understand their physical nature. We're in that strange position with dark matter, knowing it's there, understanding some of its properties, but lacking the crucial observation that would tell us what it fundamentally is. But even without that final piece, we can ask, what would happen if dark matter disappeared? If we could somehow turn off its gravitational influence, what would happen to the Milky Way? This is a thought experiment, an impossibility given the laws of physics, but instructive nonetheless. Imagine that at some moment, all the dark matter in the Milky Way simply vanished, blinked out of existence, leaving only the ordinary matter, stars, gas, dust, bound together by their own mutual gravity. What would happen? The immediate consequence would be catastrophic. The Milky Way's stellar disk is rotating at roughly 220 kilometers per second, held in orbit by the combined gravitational pull of stars, gas, and dark matter. Remove 90% of that mass, the dark matter component, and suddenly the gravitational force is insufficient to maintain these orbits. Stars in the outer regions would fly off almost immediately, flung outward like water from a spinning wheel when friction is suddenly removed. They'd escape the galaxy entirely, dispersing into intergalactic space over a few 100 million years, which is how long it takes for stars in the outer disk to complete an orbit. Stars closer to the center might remain bound, but the disk would be violently disrupted. The spiral structure we see today, maintained by density waves propagating through the disk, would dissolve. The organized rotation would break down into chaotic motions as stars adjusted to the new, much weaker gravitational field. The satellite galaxies orbiting the Milky Way would also escape. These dwarf galaxies are bound to the Milky Way's dark matter halo, not to the visible galaxy. Without dark matter, the orbital velocities of satellites like the Magellanic Clouds or the Sagittarius Dwarf would exceed escape velocity. They drift away into intergalactic space, no longer gravitationally connected to what remained of the Milky Way. Even the supermassive black hole at the galactic center, Sagittarius A*, would be affected. The stars in the innermost regions, orbiting the black hole in the nuclear star cluster, would remain bound. Their orbits are dominated by the black hole's gravity rather than the dark matter halo. But the overall structure of the galactic center, the distribution of gas and stars in the bulge region, would change as the extended gravitational potential weakened dramatically. Gas clouds in the disk would be affected differently than stars. Gas can dissipate energy through collisions and radiation, allowing it to settle into new configurations in ways stars cannot. Some gas might remain bound and continue forming stars, though at a much reduced rate without the gravitational confinement provided by the dark matter halo. Much of it would probably be expelled by supernova feedback and stellar winds, which currently drives gas outflows, but typically not to escape velocity because the dark matter halo provides sufficient gravitational pull to retain it. Within 1 billion years, perhaps less, the Milky Way as we know it would cease to exist. What remained would be a much smaller, compact system, perhaps similar to an elliptical galaxy, containing only the innermost regions where stars were originally dense enough to remain bound by their mutual gravity alone. Most of the stellar mass would be dispersed across intergalactic space, individual stars or small groups drifting through the void, orphaned from any galactic system. This thought experiment reveals how crucial dark matter is to galactic structure. The visible galaxy, the beautiful spiral of stars and gas we can photograph and study, exists only because it's embedded in a much larger dark matter halo that provides the gravitational well holding everything together. This brings us to the question we've been dancing around. Are we sure it's dark matter? Could it be modified gravity instead? Modified Newtonian dynamics, proposed by physicist Mordechai Milgrom in 1983, offers an alternative explanation. The idea is elegant. What if Newton's law of gravity itself changes at very low accelerations, below about 1/10,000,000th of a meter per second squared? At higher accelerations typical of the solar system or stellar systems, standard Newtonian gravity applies, which is why we never noticed the modification before. But at the low accelerations characteristic of the outer regions of galaxies, gravity becomes stronger than Newton's law predicts, providing the extra gravitational force that produces flat rotation curves without requiring dark matter. Milgrom's theory works remarkably well for spiral galaxies. With a single modification to gravity, you can fit rotation curves across a wide range of galaxy types and masses. This empirical success is impressive and has kept modified gravity theories alive as alternative hypotheses despite most physicists favoring dark matter. But the theory struggles with several observations that dark matter handles naturally. Galaxy clusters require more mass than can be accounted for. Even with modified gravity, you need some additional matter. Proponents often invoke neutrinos or other components, but this somewhat defeats the purpose of avoiding dark matter in the first place. The bullet cluster observation we discussed earlier, where mass and gas are separated in colliding galaxy clusters, poses a serious challenge. The lensing mass follows the galaxies, not the gas, exactly as dark matter predicts. Modified gravity predicts the gravitational field should be determined by the distribution of ordinary matter, which in clusters is dominated by gas. The observations don't match. The cosmic microwave background fluctuations and large-scale structure formation also strongly favor dark matter. The detailed pattern of temperature fluctuations observed by satellites like Planck matches simulations with dark matter extremely well. Modified gravity approaches have difficulty reproducing these patterns without introducing additional components that start to look suspiciously like dark matter under different names. Recent tests have further constrained these alternative theories. Observations of wide binary stars, pairs of stars, separated by large distances where accelerations are low enough that modifications should appear, show no evidence for deviation from Newtonian gravity at the predicted scale. This doesn't completely rule out all versions of modified gravity, as there are variants that could potentially explain these results, but it adds to the challenges. Most physicists have concluded that while modified gravity's empirical success with galaxy rotation curves is intriguing and perhaps pointing towards something we don't fully understand about the interplay between dark matter and baryonic matter in galaxies, it's unlikely to be the complete answer. Dark matter remains the strongly favored explanation because it's consistent with multiple independent lines of evidence across different scales and systems. But the fact that Milgrom's approach works as well as it does for rotation curves is a puzzle. Some researchers are exploring whether the correlation between baryonic matter distribution and rotation curves that his theory captures might be telling us something about how dark matter and ordinary matter interact during galaxy formation, even if the modification of gravity isn't the correct fundamental explanation. These questions remain open, part of the ongoing work to understand dark matter's role in galaxies. But the preponderance of evidence from cosmology, structure formation, gravitational lensing, galaxy clusters, and the cosmic microwave background points toward dark matter being real particles, not a modification of gravity. Let's step back and consider what it means to live in a universe dominated by dark matter. If dark matter didn't exist, if the universe contained only ordinary matter, what we see through telescopes would be all there is. That universe would be very different from the one we observe. Structure would have formed more slowly, if at all. Galaxies might be rare, small, and loosely bound. The cosmic web might not exist. Stars might form in isolation rather than in galactic systems. The fact that dark matter exists and dominates cosmic mass means we live in a universe where structure can form efficiently, where gravitational instability can operate over cosmic time to build galaxies and clusters, where matter can organize itself into the rich hierarchy of structures we observe from dwarf galaxies to superclusters. Dark matter also means we live in a universe that is fundamentally mysterious in deep ways. Despite centuries of scientific progress, despite our ability to peer back nearly to the Big Bang, to observe galaxies billions of light years distant, to understand stellar evolution and nuclear physics and general relativity, fundamental questions remain unanswered. The Milky Way, our home galaxy, the structure within which the Sun orbits, within which all the stars visible to the naked eye reside, this structure is held together by something whose identity remains unknown. Every orbit the Sun completes around the galactic center depends on dark matter's presence. Yet, in another sense, this is liberating. The universe still holds fundamental secrets. There are still deep questions to answer, mysteries to solve. The cosmos remains larger and stranger than our current understanding encompasses. The search for dark matter's identity continues in experiments deep underground, in particle accelerators smashing protons together at near-light speed, in space telescopes measuring gamma rays from the galactic center where dark matter might annihilate, in theoretical physics papers exploring new mathematical frameworks. It's one of the great scientific quests of our era. Perhaps that final piece will come from the next generation of direct detection experiments, with sensitivity improved by orders of magnitude. Perhaps it will come from particle accelerators finding supersymmetric particles or other new physics beyond the standard model. Or perhaps it will require theoretical breakthroughs, new ideas about how to search that haven't yet been conceived. Whatever form the answer takes, it will transform our understanding of fundamental physics. It will reveal new particles, new forces, new principles operating in nature. It might connect to other mysteries: why matter dominates over antimatter in the universe, what happened in the first moments after the Big Bang, how quantum mechanics and gravity will ultimately be unified. The Milky Way, held together by invisible hands, serves as a laboratory for exploring these questions. Every measurement of stellar velocities, every satellite galaxy orbit traced, every gravitational lensing signal detected adds another constraint on dark matter's properties, another piece of the puzzle. We're fortunate to live in an era when this mystery is approachable but not yet solved. When the question is profound but not hopeless. When experiments are ongoing and discoveries possible. Future generations might look back on this time with envy, wishing they could experience the excitement of discovering dark matter's nature for the first time. The way we envy physicists who first understood nuclear fusion or discovered the cosmic microwave background. The search for dark matter is entering a new phase, with experiments of unprecedented sensitivity coming online and new observational techniques revealing galaxy properties in greater detail than ever before. On the direct detection front, next-generation experiments are being planned with masses in the tens of tons, approaching the scale where sensitivity reaches the neutrino floor, the point where background from neutrino interactions becomes irreducible and detection becomes significantly more challenging. These experiments, like Darwin and XLZD, will probe WIMP parameter space comprehensively over the next decade. If WIMPs exist in the theoretically favored mass range and interact at rates anywhere near current expectations, these experiments will find them. If they don't, if the next generation of experiments also returns null results, it will force serious reconsideration of the WIMP paradigm. This doesn't mean dark matter doesn't exist. The astrophysical evidence is too strong, but it would mean we've been looking in the wrong place or for the wrong type of particle. Attention would shift more strongly to alternatives like axions, which require different detection techniques, or to the possibility that dark matter is far more weakly interacting than even pessimistic WIMP models predict. Axion searches are also advancing rapidly. The ADMX experiment is systematically scanning through possible axion masses using resonant microwave cavities in strong magnetic fields. Each frequency requires dedicated running time, making the search slow but thorough. Future experiments will expand the search to different mass ranges and use multiple detection techniques to cover more parameter space. Space-based observations continue to provide complementary approaches. The Fermi Gamma-ray Space Telescope and upcoming missions search for gamma-ray signals from dark matter annihilation in the galactic center, dwarf spheroidal galaxies, and galaxy clusters. While no convincing signal has been found, Upper limits continue to constrain dark matter annihilation rates, providing astrophysical constraints on particle physics models. The European Space Agency's Euclid mission, launched in 2023, is mapping billions of galaxies to study dark matter through gravitational lensing on unprecedented scales. By measuring how galaxy shapes are distorted by foreground dark matter, Euclid will create three-dimensional maps of dark matter distribution across cosmic time, revealing how structure has grown and evolved over billions of years. Euclid's survey will cover more than a third of the sky, observing galaxies out to distances where we see them as they were 10 billion years ago, when the universe was less than a quarter of its current age. This time machine aspect of cosmology allows us to watch structure formation in action, to see how dark matter halos grew and merged over cosmic history, to test whether our theoretical models of structure formation match reality across different epochs. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will provide complementary observations with different capabilities. Roman's wide field of view and sensitivity will allow it to study dark matter through multiple techniques simultaneously: gravitational lensing to map the distribution of matter, galaxy clustering to understand how galaxies trace dark matter structure, and direct observation of satellite galaxies in the local universe to probe dark matter substructure. One particularly exciting capability of Roman will be its ability to conduct massive surveys of the galactic center and bulge regions of the Milky Way. These areas, obscured by dust at optical wavelengths, become visible in the infrared light that Roman specializes in. By mapping millions of stars in these crowded regions, Roman will provide crucial data about the dark matter distribution in the inner galaxy, where the density is highest and theoretical uncertainties are greatest. Ground-based surveys like the Vera-C, Rubin Observatory's legacy survey of space and time, which began operations in 2024, will discover thousands of new faint satellite galaxies around the Milky Way and other nearby systems. These satellites serve as tracers of dark matter substructure, testing simulation predictions and potentially revealing signatures of dark matter's particle nature through their internal structure and dynamics. The Gaia mission continues, providing ever more precise measurements of stellar positions and velocities throughout the Milky Way. As the mission duration extends, the data quality improves, allowing astronomers to measure subtle perturbations in stellar orbits that might reveal dark matter substructure, to map the three-dimensional gravitational field of the galaxy in unprecedented detail, to discover more stellar streams and use them to constrain the dark matter halo's shape and mass. On the theory side, computational simulations are reaching new levels of sophistication. Modern cosmological simulations track billions of particles and include detailed treatment of star formation, supernova feedback, black hole growth, and other baryonic processes that affect galaxy formation. These simulations can resolve structures down to dwarf galaxy masses and below, testing whether small-scale problems like the missing satellites and core cusp issues can be resolved through better understanding of galaxy formation physics or whether new dark matter physics is required. Some simulations are exploring self-interacting dark matter models, where dark matter particles can scatter off each other through a new force beyond just gravity. These models can potentially solve the core cusp problem by redistributing dark matter in galaxy centers while maintaining consistency with larger-scale observations. Future observations of galaxy mergers and cluster collisions could test whether dark matter exhibits the self-interaction signatures these models predict. Machine learning and artificial intelligence are being applied to dark matter searches in innovative ways. Neural networks trained on simulations can identify subtle patterns in observational data that might indicate dark matter substructure or novel properties. These techniques are being used to optimize detector designs, to search for anomalies in large datasets, to connect observations across different scales and wavelengths. The field is also grappling with what null results might mean. If the next 20 years of experiments find no dark matter particles, what are the alternatives? Would we need to revisit fundamental assumptions? Consider more exotic possibilities like dark matter being a quantum field phenomenon rather than particles, or being composed of black holes from the early universe after all, or being something even stranger we haven't yet imagined. These questions motivate continued investment in diverse approaches. Rather than putting all resources into one type of experiment or one theoretical framework, the community is pursuing multiple avenues simultaneously. If dark matter turns out to be axions rather than WIMPs, we'll have experiments ready to find them. If it's something completely unexpected, the broad range of observations across astrophysics and cosmology will provide clues to guide us toward the answer. There's another aspect of dark matter we haven't fully explored yet, one that reveals its influence not just on galactic structure, but on galactic evolution over cosmic time. Dark matter doesn't just hold galaxies together statically, it actively shapes how they grow, interact, and transform across billions of years. When two galaxies collide and merge, as happens frequently throughout cosmic history, their dark matter halos merge as well. These mergers are among the most dramatic events in the universe, reshaping galactic structure on timescales of hundreds of millions to billions of years. But the visible fireworks, stars scattered into tidal tails, gas clouds compressed to trigger starbursts, supermassive black holes spiraling together represent only the visible component. The bulk of the mass, the dark matter, merges through a different process. Dark matter halos, composed of collisionless particles, interpenetrate during mergers. Unlike stars, which can collide directly, or gas, which creates shock waves and dissipates energy through radiation, dark matter passes through itself. Individual dark matter particles from the merging halos thread through each other like two schools of fish swimming past each other, only gradually settling into a new equilibrium through gravitational interactions alone. This process, called violent relaxation, takes time. During the merger, the gravitational potential fluctuates wildly as mass concentrations shift and redistribute. Dark matter particles respond to these changing potentials, their orbits transformed by the time-varying gravitational field. Over hundreds of millions of years, the system reaches a new equilibrium, a single, larger dark matter halo containing both progenitor halos' mass. The physics of this process is fascinating in its own right. When dark matter halos merge, they don't simply add together like mixing two buckets of water. The gravitational interactions during the merger are complex and nonlinear. As the two halos approach each other, tidal forces begin to distort their shapes. The outer regions of each halo, where the density is lowest and particles are most loosely bound, are stripped away first, forming streams and bridges of dark matter connecting the two galaxies. These tidal tails of dark matter can extend for hundreds of thousands of light years, invisible traces of the gravitational violence occurring during the merger. While we cannot see the dark matter directly, we can sometimes observe its effects. Stars that were in the outer regions of the merging galaxies follow trajectories shaped by the dark matter distribution, creating stellar streams that trace the underlying dark matter structure. By mapping these stellar streams, astronomers indirectly map the dark matter, revealing the complex choreography of merging halos. As the merger proceeds, the cores of the two dark matter halos, where the density is highest, resist disruption longer. They spiral inward through a process called dynamical friction. Imagine trying to move through a crowded room. You're slowed down by gravitational interactions with all the people you pass. Similarly, each dark matter halo experiences drag from gravitational interactions with the other halo's particles, causing the halos to lose orbital energy and spiral together. The time scale for this spiral depends on the masses involved and the initial orbital parameters. For major mergers where the two galaxies have comparable masses, like the future Milky Way Andromeda collision, the spiral might take 1 to 2 billion years after the first close encounter. For minor mergers where a small dwarf galaxy falls into a large galaxy, the process can be faster, perhaps a few 100 million years. Eventually, the two cores merge completely, their dark matter particles mixing thoroughly through phase space. The result is a single dark matter halo, with properties determined by the progenitor's masses and orbital characteristics. If the merger was head-on, or nearly so, the final halo might be quite spherical. If the merger involved a grazing collision or significant angular momentum, the final halo might be somewhat flattened or elongated, at least temporarily, until further relaxation makes it more spherical. The Milky Way has experienced numerous such mergers throughout its history. Each infalling dwarf galaxy brought its own dark matter halo, adding mass to our galaxy's growing halo. The largest recent merger, Gaia Enceladus, added perhaps 10 to 20% of the current stellar mass and a comparable fraction of dark matter. Earlier in the galaxy's history, when it was still assembling, mergers were even more common and more massive, each adding substantial dark matter along with stars and gas. We can read this merger history in the structure of the dark matter halo today. Just as archaeologists excavate layers of sediment to understand a site's history, astronomers study the phase space structure of the stellar halo, the positions and velocities of stars to reconstruct the Milky Way's merger history. Stars from different merger events have different orbital characteristics, different chemical compositions, different ages. By identifying these populations, we identify the merger events that brought them into our galaxy. And where there are stellar remnants of ancient mergers, there must also be dark matter remnants. The Gaia sausage, that elongated distribution of stars in the inner halo, is accompanied by dark matter from the same merger event. Other substructures, streams, and overdensities in the dark matter distribution trace back to similar events billions of years ago. The halo is an archaeological record preserving information about the galaxy's merger history in its structure, written in the motions and distributions of both stars and dark matter. These merger events also affected the Milky Way's disk. When a satellite galaxy plunges through the disk, the gravitational perturbation creates waves ripples in the stellar density that propagate outward like ripples on a pond. These waves have been detected in recent years using Gaia data, revealing that the disk is not in perfect equilibrium but still responding to ancient perturbations, possibly from the Sagittarius dwarf galaxy's repeated passages through the disk over the past few billion years. The dark matter from infalling satellites also contributes to these perturbations. As a satellite's dark matter halo passes through the disk, it creates a gravitational wake, disturbing the orbits of stars and the distribution of dark matter already present. These disturbances can persist for hundreds of millions of years, creating long-lived structures in the phase space distribution of both stars and dark matter. Looking forward, the Milky Way will experience another major merger in about 4 to 5 billion years when the Andromeda galaxy, currently approaching at about 110 kilometers per second, collides with us. This merger will be spectacular from the perspective of visible astronomy, assuming there are astronomers around to observe it with tidal tails of stars stretching across hundreds of thousands of light years, gas compression triggering waves of star formation, and the two supermassive black holes eventually spiraling together and merging. But the dominant mass component of this merger will be the dark matter. The Milky Way's dark matter halo, containing perhaps 1 trillion solar masses, will merge with Andromeda's similar-sized halo, creating a single enormous halo containing roughly 2 trillion solar masses of dark matter. This merged halo will extend to millions of light-years, dwarfing the visible remnant galaxy that forms from the stellar components. The visible galaxy resulting from this merger will likely be an elliptical galaxy, its stellar disk disrupted by gravitational interactions and transformed into a roughly spherical distribution of stars. The beautiful spiral structure we see today will be erased, replaced by a smooth, featureless elliptical. But the dark matter halo, it will remain what it's always been, a roughly spherical distribution, extending far beyond the visible galaxy, providing the gravitational framework within which the visible structures exist. Computer simulations can predict the details of this merger with remarkable precision. By inputting the current positions, velocities, and mass distributions of the Milky Way and Andromeda, including their dark matter halos, simulators can evolve the system forward in time, watching the merger unfold. These simulations show the first close passage occurring in about 4 billion years, with the galaxies swinging past each other, exchanging gravitational energy stretched into long tidal tails. Then they fall back together for a second passage, and eventually merge completely after multiple close encounters spanning perhaps another billion years. Throughout this process, the dark matter halos do most of the gravitational work. The visible galaxies, the disks of stars and gas we can see, contain only a small fraction of the total mass. It's the dark matter that determines the orbital dynamics, the merger timescale, the final configuration. The visible matter responds to gravitational fields created primarily by dark matter, settling into configurations determined by the dark matter distribution. This merger between Milky Way and Andromeda is just one example of countless galaxy mergers occurring throughout the universe at every moment. In the early universe, when galaxies were closer together and mergers more common, the merger rate was much higher. Galaxy evolution was dominated by these interactions, with most galaxies experiencing multiple major mergers as they assembled from smaller progenitors. Observations confirm this picture. When astronomers look at distant galaxies, observing them as they were billions of years ago, they see more irregular structures, more evidence of ongoing interactions and mergers, fewer well-defined spiral galaxies like we see nearby. The universe's galaxy population has evolved over cosmic time, driven largely by mergers orchestrated through dark matter's gravitational influence. Computer simulations of galaxy mergers that emit dark matter produce results that look nothing like observations. The dynamics are wrong, the timescales incorrect, the final structures unrealistic. Include dark matter with the observed abundances and distributions, and suddenly the simulations match observations remarkably well across a range of galaxy types and merger configurations. This provides yet another line of evidence for dark matter's existence and properties. Galaxy mergers are common throughout cosmic history. We observe them at all stages, from initial approach to final coalescence. The fact that these observations match simulations, including dark matter, but not simulations without it, is powerful confirmation that dark matter is real and that we understand its basic properties correctly, even if we don't know what it's made of. We've journeyed from rotation curves to gravitational lensing, from particle physics to computer simulations, from the cosmic microwave background to stellar streams in the Milky Way's halo. Through all of this, dark matter has been the invisible thread connecting observations across vastly different scales. Darkness isn't absence. Dark matter is real, material, substantial. It shaped the universe's evolution from the smooth early cosmos to the structured present. It enabled galaxies to form, allowed stars to be born, created the conditions for planets, and ultimately, life to emerge. In this sense, dark matter is essential to our existence. The atoms that make up your body were forged in stars that formed in galaxies held together by dark matter. The cosmic evolution that led to Earth, life, and consciousness was fundamentally shaped by dark matter's gravitational influence. There's something profound about this dependence we have on something we cannot perceive directly. Every moment of human history, from the first self-aware thoughts of our ancestors to the present instant as you engage with these words, has unfolded within a dark matter halo. Every human achievement, every work of art, every scientific discovery, every act of love or courage or creativity, all of it occurred while embedded in this invisible ocean of particles streaming through us constantly. We are, in a very real sense, creatures of darkness, not in any sinister meaning, but in the literal sense that our existence depends on structures formed and maintained by dark matter. The stable galactic environment that allowed our solar system to form and persist for 4.5 billion years without major disruptions exists because the Milky Way's dark matter halo provides gravitational stability. The relatively calm neighborhood we occupy, away from the chaotic galactic center and the sparse outer regions, exists within a gravitational landscape shaped primarily by dark matter. Even the elements that make up your body have a connection to dark matter that goes deeper than you might initially think. Yes, these elements were forged in stars, but those stars formed in molecular clouds that collapsed under gravity, amplified by dark matter's presence. The rate of star formation in the Milky Way over billions of years, determining when and where stars like our Sun would form, was influenced by the dark matter distribution and its gravitational effects on gas dynamics. Consider the iron in your blood, allowing oxygen to flow through your body. That iron was created in the core of a massive star that eventually exploded as a supernova, scattering heavy elements into space. But that star formed in a galaxy held together by dark matter. The calcium in your bones, the carbon in your organic molecules, The oxygen you breathe, all of these elements trace their origins to stellar nucleosynthesis occurring within galaxies bound by dark matter. You are, quite literally, made of stardust that exists because dark matter made galaxies possible. This creates a strange tension in our understanding. We know the story of how structure formed, how galaxies evolved, how the Milky Way came to have its current properties. But there's a character in this story whose identity we haven't discovered, whose nature remains hidden. Perhaps this is appropriate. The universe should be allowed its mysteries, its secrets that resist easy discovery. The fact that reality contains aspects beyond our current comprehension that require decades of effort and ingenuity to uncover makes the cosmos more interesting rather than less. It keeps us humble, reminds us that human knowledge, however impressive, remains incomplete. There's a peculiar beauty in this state of partial knowledge. We understand enough to ask sophisticated questions, but not enough to answer them completely. We can trace the consequences of dark matter across cosmic history, from the first moments after the Big Bang to the present day, following its gravitational influence like following footprints in snow, clear evidence of something passing by, even if we never see the thing itself. This puts us in a unique position in the history of human thought. For most of history, our ancestors looked at the night sky and wondered about distant lights they could barely comprehend. They invented myths and stories to explain what they saw, attributing the motions of stars and planets to gods and spirits, weaving narratives that made sense of the mysterious lights above. We've progressed far beyond that. We understand stellar evolution, galactic dynamics, cosmology. We can predict precisely where planets will be decades or centuries from now. We've measured the age of the universe to within 1%, determined its composition, traced its evolution from initial conditions to present structure. Yet we face a mystery that would have been incomprehensible to our ancestors, not a mystery about what we can see, but about what we cannot see. What dominates the cosmos but remains invisible to all our instruments except through its gravitational effects? The ancient philosophers who looked at the night sky and wondered about the nature of the cosmos would probably be amazed by how much we've learned the distances to stars, the lifetimes of galaxies, the age of the universe itself. But they might also recognize in our dark matter problem an echo of their own confrontation with cosmic mysteries that seemed beyond human reach. The difference is that we have tools they lacked. We have mathematics that allows us to model gravitational dynamics precisely. We have telescopes that collect photons from across the electromagnetic spectrum. We have particle detectors capable of sensing individual interactions. We have computers that simulate galaxy formation across cosmic time. These tools give us power to probe the darkness, to constrain what dark matter can and cannot be, even if we haven't yet identified it directly. And we have something else they lacked: a community of thousands of scientists worldwide working collaboratively on these problems, sharing data across international borders, building on each other's work, gradually constructing a collective understanding that transcends any individual's contribution. The search for dark matter is a global effort, with experiments on multiple continents, observations from telescopes in space and on Earth, theoretical work spanning multiple universities and research institutions. This collaborative nature of modern science means that when the answer comes, when we finally identify what dark matter is made of, it will belong to humanity as a whole, not to any single person or nation. It will be a triumph of collective human curiosity and ingenuity, built on decades of work by thousands of people, each adding their piece to the puzzle. The search continues. Experiments run deep underground, collecting data night after night, waiting for the rare dark matter scatter that would announce the discovery. Telescopes survey the sky, measuring galaxies and mapping mass distributions. Theorists calculate, exploring the implications of different dark matter models, making predictions that observers can test. The worldwide scientific community works collectively on this problem, sharing data, comparing results, building incrementally toward understanding. When the answer comes, and it will come, whether in 5 years or 50, it will transform physics. It will reveal new aspects of nature, new particles or phenomena not included in our current theories. It will connect to other mysteries, providing insights that ripple through multiple fields. It will be celebrated as one of the great discoveries of the 21st century, perhaps as significant as the discovery of the electron or the neutron, as transformative as understanding nuclear fusion or detecting gravitational waves. But until then, we live in a galaxy held together by invisible hands. We orbit through space at 220 kilometers per second, carried along by the sun's motion through the dark matter halo, completely unaware in our daily lives of the cosmic infrastructure supporting everything. The Milky Way rotates, the spiral arms persist, stars are born and die, all within a gravitational framework constructed from matter we've never seen. It's both humbling and exhilarating. Humbling because it reveals how much we don't know, how much of the universe operates according to principles we're still working to understand. Exhilarating because the mystery is tractable, because we're making progress, because every observation adds another piece to the puzzle. The dark matter holding the Milky Way together is real. It's here, around us, through us, a constant presence in every cubic meter of space. Someday, we'll know what it is, understand its properties at the fundamental level, perhaps even manipulate it or use it in ways we can't currently imagine. But for now, it remains the universe's greatest hidden mass, the invisible majority, the dark foundation upon which visible reality rests. Look up on a clear night. See the Milky Way stretched across the sky, that river of stars that gave our galaxy its name. Remember that what you're seeing is just the foam on the surface, just the visible minority. Most of what holds it all together lies hidden in darkness, substantial and real but invisible, felt only through its gravitational embrace. That darkness is not emptiness. It's matter, real and consequential. It's the scaffolding of cosmic structure. It's the answer to a question we haven't fully formulated yet, waiting in the data from experiments and observations, waiting to be discovered. And when we finally understand it, when the identity of dark matter is revealed, it will be because of human curiosity and ingenuity, because of the drive to understand the cosmos we inhabit, because we looked at the night sky and asked not just what we could see, but what must be there that we cannot see, what invisible architecture underlies the visible beauty of stars and galaxies. The Milky Way continues its slow rotation through cosmic time, held together by gravity from matter both seen and unseen. We're privileged to live within it, to orbit a star embedded in its disk, to have the intellectual tools and observational capabilities to study its structure and evolution, to probe the invisible halo surrounding it, to ask questions about its nature that our ancestors could never have conceived. Thank you for spending this time exploring the darkness with me. If this investigation has expanded your sense of what exists in our galaxy, if it's revealed some of the invisible structure underlying the cosmos we inhabit, I'm grateful you've been part of this journey through the Milky Way's dark matter halo. The search continues, the mystery endures. But we're closer than ever to understanding what holds our galaxy together, what shapes the universe on its largest scales, what most of the matter in the cosmos actually is. Someday, perhaps soon, the darkness will reveal its secrets. Until then, we observe, we calculate, we search, we wonder.